Volume Podcast.
Hi, my name is Rupal Srivastava, and I am a PhD student at Indian Institute of Technology, Kanpur. I'm just completing my PhD, so I'm awaiting my defense, and I will be joining as a postdoctoral fellow at the Smart Manufacturing Research Center, which is a Science Foundation Ireland funded lab. And my interests are working on smart materials, a little bit its application towards robotics in structures and shape and vibration control with metamaterials, things like that. So mechanical engineering in general.
Hi, Rupal. So this is a very interesting and very vast field of study. So what's in you that drove you to research this subject?
So the interest, I won't say was in this field per se. During my master's, I felt very comfortable with the routine and with the idea of research, and I was very curious about having an opportunity to study and to gain knowledge. And whatever I was working on, I was working for kind of myself. So the idea was to choose between research and corporate, and the flexibility and the opportunity to learn, those were more in research. And that is why I took 6 months break after my master's to decide that, yes, I have to get into a PhD program. So we have entrance exams here, and once we get into a college, we then have to complete a coursework. And during that coursework, we have to choose a supervisor from the department. So it's not the other way around that we look into labs or supervisors. We actually clear entrance exams for PhDs in IITs. So I chose the IIT, which was the closest to my family, because it's a long-term commitment and I wanted to be somewhere closer to my family. And I chose my supervisor based on how kind and how student-friendly he was, and also because he had these projects from all the prestigious organizations in the country. He had an ISRO project, he had project from GAIL, which is the Gas Authority of India. So that is the reason why I started to work with him, because it obviously had the ISRO project. And I think growing up, ISRO is the dream of each and every engineer or science student in the country. So I started to work on this ISRO project, and it was kind of replicating the inflatable antenna experiment done by NASA in 1990s. And it not experimentally, but making the numerical model of it. So I was working on its numerical model, and the reason why we were trying to replicate that experiment was because that was a very budget project. And as a developing country, we are always seeking ways to make technology more and more under budget. So that is the reason why I was working on that project, and why that project was given to us. And while working on the project, I found that there were many challenges involved. So we have this torus-shaped inflatable structure, which is the the structure which kind of bears all the load for the reflector part of the antenna. And then there are these struts which are attached to this torus, and those struts are then attached to a box. So this entire strut, torus, and the antenna reflector part, they're all stored in that box, and they are then sent to space, and then they are inflated there and deployed there, and then the entire structure is made up. So there were many issues with the torus structure, the inflatable part. So the first one was that the inflatable structures usually, because of the space debris, can experience degassing. And then because of the shadowing, the rigidization of those torus structures, they can be uncontrolled, and the inflation was uncontrolled. So while working on that, we also started to look into these challenges and a possible solution to it. And the solution also had to be a budget solution and a sustainable solution. And also, not only should it solve all the challenges, but it also, if possible, could have been a reversible process. So that is when we got into smart materials and seeking ways to replicate that inflation and rigidization process without the need of gas, and have some sort of shape and vibration control of it. So this is how I got into this field. So it wasn't that I was looking into smart materials and then I pursued it. It's just that I was looking for PhD, I was looking for research, and during that research, we got into this field.
So what is shape memory alloys, and what are those smart materials?
So shape memory alloys, these are special kind of metallic alloys. So they have this special property, two special properties actually. One is the shape memory effect, also called the thermal shape memory, and the other one is superelasticity. So with the thermal shape memory, how it works is that the shape memory alloy, it exists in two phases at different temperatures. Martensite phase and austenite phase. These phases are actually crystal or lattice structures of the molecules in that alloy. So at lower temperatures, the shape memory alloys, they are in their martensite phase, and which is a close, loosely packed and kind of a flexible phase. The material is very flexible, and at high temperatures, it is in its a stiff austenite phase, more tightly packed. So utilizing this property, what people can do is that as we increase the temperature from room temperature to, let's say, 60 degrees Celsius or 70 degrees Celsius, the material is going to change its phase. And if, in case of shape memory alloys, if we train them to a certain shape, to take a certain shape in its austenite phase, so what happens is that in martensite phase, you can play around with the material. You can kind of pull it, you can mold it into some other shape, you can tie a knot if it's a wire, and as soon as you increase the temperature and it reaches its austenite phase, it will take the shape that we desire. So it might become a plate, it might become a bowl, whatever shape we train it to be. So this is the thermal shape memory effect. The other one is superelasticity. So what happens in superelasticity is that when the material is already in its austenite phase, then it can undergo a huge amount of deformation without plastic deformation, which means that as soon as we remove the load, it will get back to its original shape. So based on this, for thermal shape memory effect, there are many applications. One of them is what I am trying to do is that as I actuate, it will change its shape, and by changing its shape, it will move the other material or the structure which is kind of integrated with it. So by changing its shape, I'm contracting it. And a very interesting application of superelasticity is the reinventing of the wheel. So the Mars rover, they have these wheels which are made of steel meshes, and they are meshed. And by reinventing it, what we are doing is that we are replacing steel with nickel titanium alloys, which are shape memory alloys, and we are making the meshes out of this alloy. So what happens is that in space, on Mars, because the terrain is very uneven and there is no one to kind of repair it, so they can undergo huge amount of deformation and they will still be workable. So they will still retain the shape that they were trained in, and the wear and tear will be less and less. So there are many applications, and in dentures we have, for the dentures, if they are trained to take a certain shape of our teeth along our jawline, so we need not go to the doctor and get it tightened at each and every sitting. So it will continuously keep getting back to its shape. So there are many uses of superelasticity and also for thermal shape memory effect. In our case, we are taking these wires, these shape memory alloy wires or nickel titanium wires, which are the most popular shape memory alloys, and they are trained to contract. So we kind of pre-string it. So in its martensite phase, if they are, let's say, some length, and as we heat it up, so they can contract up to 5% of their original length. So if we integrate them at an offset in a composite, what will happen when we are going to heat it? The shape memory alloy is going to contract, but because the rest of the material, the rest of the composite is not going to contract, so the entire composite is kind of going to bend with it. So using this property, we can then kind of get a cylindrical shape or a saddle shape or a dome-like shape from these structures based upon what the composite constituents are. So that's how we are kind of getting different elements of the torus. And once we have the different shapes, for example, for a torus, we basically need three shapes to make the entire structure. One is zero Gaussian curvature, which is a simple cylindrical shape. Then we need a positive Gaussian curvature, which is a dome-like shape or a synclastic shape, as we call it. And the third one is the negative Gaussian curvature, which is the saddle shape behavior that we can see as a horse saddle. So these three shapes make a torus. And in my research, this is what I have done. I have used shape memory alloys integrated with different kinds of composites to get these three curvatures and to, in the end, form this torus shape. And it will now remove the requirement of inflation and rigidization using UV curable resins. So, and that's what my research is. In the composites in which I have embedded shape memory alloy wires, they are of several types, but one of the very interesting ones is embedding them with auxitic structures. These auxitic structures have negative Poisson's ratio. What that means? It means that the conventional materials which we see in our everyday lives is when we pull them in one direction, they kind of thin down in another direction. So if we have, let's say, an elastic band and we stretch it, what is going to happen? It's going to get thinner and thinner and eventually break. But in these auxitic structures or auxitic metamaterials, as we call it, when we pull them in one direction, if we call this a longitudinal direction and perpendicular to it, the transverse direction. So if we pull it in longitudinal direction, it is going to expand in its perpendicular direction. So it's a very interesting material. So we can work with the structures also, we can work on its microstructure also. And using them kind of gives us the synclastic behavior that I was talking about, the dome-shaped behavior. So these are some very interesting materials which I would really want whoever is listening to this to look into. Those have a range of applications, and these are the materials which are of future, auxitic metamaterials.
So these materials came into your life as a research opportunity, but after researching and working with them, you probably have some very interesting ideas of future use of special materials. So how did this change your vision of the world in a way?
Yes, I think earlier I was only interested in research, in the lifestyle of research, in the idea of learning and gaining knowledge and having the flexibility of working on my own project. But now the idea has shifted from that kind of comfort zone and just the idea of learning, and it has moved to finding solutions. So in huge projects, it's possible that there can be just a tiny or a small improvement, or kind of we can get an alternative and we can change the behavior of it, the efficiency of it, and the expense of it considerably. So now the idea is to find challenges or the gaps in the existing research and to fill them, and also to have more and more creative ideas using shape memory, not just shape memory alloys, smart materials. So these can be piezoelectric materials, magnetostrictive materials. So in general, making things more and more smart, keeping budget and sustainable development in mind.
And nowadays, where can we find products made using this type of materials?
Okay, so one of the commercial use of shape memory alloys is in dentures and in these stents. So there are these shape memory alloy based stents, nitinol stents, because nitinol or nickel titanium alloys are medical grade. So these stents, they are now being used as catheters and also for bypass surgeries. So what we do is that we are now utilizing the super elastic behavior of shape memory alloys, and so we are kind of contracting the stent and then pushing it inside the veins. And as soon as that load is removed, it takes the shape that we have trained it for. And the fat that is accumulated in the veins, which is blocking the vein, it is pushed back towards the walls and the blood flow becomes more and more normal. So it's not a permanent solution, but for the time being, while the operation is going on and things like that, this method is being used. And the other use that that I have proposed for the postdoctoral position is use of shape memory alloys for rehabilitation purposes in smart wearables. So we have these smart gloves, or we have smart textiles, and using shape memory alloys and then kind of creating a human-robot interaction can help people who have problem communicating, or maybe have problem. I do not want to say disabled. I want to say who are unable to do certain activities which we find very normal in our day-to-day lives. So these materials are now being used for in medical field and in robotics. So that's how these materials can find their application in our day-to-day lives. And yes, so that.
And how about future applications? How do you see this technology in 10 years?
There are many applications which I already have ideas for in earthquake engineering. So using shape memory alloys in foundations, so that when the earthquake comes, we can actively control the vibration of the building, and then we can eventually avoid failure. So that is one application which we can see in our day-to-day lives. And then I was also thinking of using these interactive materials for maybe an immersive environment project, and also for smart toys, which can be used by maybe dyslexic or autistic children. And then we can study their level of comfort with these toys, and if these toys can help them de-stress and help them with their everyday life. So there are many applications which we can envision using shape memory, not just shape memory, but smart materials in general. These are some of the projects that I personally would like to work on. And apart from that, I think that currently we have these multi-mechanism projects. So when I was talking about smart gloves, so there are DC motors, there are sensors, there are actuators, and using just shape memory alloys are going to remove so many mechanisms. So not only it is going to reduce the weight, it is also going to reduce the expense and also reduce the use of rare earth materials. So I think in future, as we move more and more towards a sustainable future, given the current scenario, I think using these materials as and when required and seeking solutions to replace the current technology, which is not as good for the environment, with these materials is going to be beneficial for the humankind, for the environment, and also it will be more and more budget oriented.
So those were my questions, but I feel the urge to ask you, was there anything that we didn't touch on or something that we should talk about that we have not talked about yet?
So yeah, I mean, there are two things that I would like to have a giveaway from this talk. The first one is more and more women in engineering, because it's kind of a taboo, or not taboo, or a stigma attached that if a woman is in mechanical engineering. So just a couple of months ago, I had this question on Quora, and there was this girl asking whether I should get into mechanical engineering because there is so much field work. Do we have to go to the manufacturing lines? Do we have to stand in companies, industries, in the manufacturing units? And they're very afraid of this field work, and they're afraid of mechanical engineering and core mechanical fields in general. So I would like to tell them that not all fields and not all topics will require a field work, and even if it does, it is doable, and it's high time that we should move from home to industries and get into STEM. And the other thing that I would like to like for people to take away from this talk is to not create problems and then find solutions to it. Instead, seek what are the problems which are in the existing technology, and then to modify it, to improve it with creative ideas which are under budget and which are not as complicated. And because nowadays I see so many people who first kind of just envision that I want to do this, they do that, and then they afterwards think about the application of that project. So that is also happening. And then, for example, like the several projects which are going on, which are irrelevant, for example, autonomous of so many things in this country, where in India, we are not short of any kind of workforce. So we should be less and less driven towards just random projects and random research. It should be more, we should have more introspection and think what we are moving towards, what we seek, what we need, what we want to improve.
Rupal, this was extremely interesting, and I learned so much today. I'm sure a lot of our listeners learned a lot as well. Thank you so much. I really appreciate you taking your time to talk to us.
Really, thank you for inviting me, and I'm happy to talk about my field of interest. And also thank you to Larissa for recommending me for this podcast.
Säkert. We love it. The Volume Podcast.
Hi, if you enjoyed this episode and would like to get in touch with us, maybe make a suggestion or ask a question, please find us on Twitter @Volume Podcast. Thank you.